Okay, for our final example, I have an admittedly totally made up report. So this is not true. These are not real statistics, but a pretend experiment in which children were randomly assigned into a new intensive preschool and others into a regular preschool. And then it was noted whether or not each child had a felony conviction by the age of 21. Okay, so with our null being that preschool type and felony conviction are not associated, and our alternate being that they are, we're going to first use the chi-squared test for independence and a significance level of 0.05 to test this hypothesis. Okay, I have already entered this information in my StatCrunch. So I'm going to go through and we're going to actually run both tests, and what's neat is that you can run them both at the same time if you want to. So I guess I'll just go ahead and do that. I'm going to choose my variables, choose my label, and you can check both of these. So I'm going to run both chi-squared test and Fisher's exact test. Okay, so what I want to look at right now is this middle box that has the chi-squared test information, and I'm going to record that chi-squared value and that p-value out of those. So the chi-squared value came out as 4.29 and the p-value came out as 0.0383. So based on this, P came out smaller than 0.05, so we would reject the null. We would reject this idea and claim that pre-K type and felony conviction are associated. Now, if we do the exact same comparison but with Fisher's exact test, so if I flip back over and look at the Fisher's exact test results, I get a p-value there of 0.0531. So in this case, I have p being ever so slightly but still bigger than 0.05, so I would fail to reject the null. So I would fail to reject it, and this time I would conclude the exact opposite, that pre-K and felony conviction are not associated. So if we compare these two, the p-values are, it's clear that the Fisher's exact one came out larger in this case, but which test is more accurate? Fisher's test always. That's the exact p-value for this case, not just an estimate. And these were fairly small sample sizes, right? And if I go back and if I go here, I'm going to go back into my options and I'm going to have it display the expected counts. Now the expected counts, they all hit. They were all over 5. So I should be good on the chi-squared test. But this is just kind of a, hey, most of the time running the chi-squared test is fine, but just remember that it is an approximation and it leaves the door kind of open for mistakes. Now, here's the most important thing to note, is that these two tests do not always produce different results. I rigged this one on purpose. I rigged those numbers so that there would be enough difference in the two p-values to give us a different result. So they don't always. A lot of times, even though the chi-squared p-value is an approximation, usually it results with the same exact overall conclusion as Fisher's exact test. It usually does. Again, I had to work really hard making those numbers work out so that they would give you different results. But I wanted you to see that it is possible that if the numbers are kind of strange enough, if they fall just the right way, that the two p-values will be different enough that they could give you different overall answers. So when your sample sizes are small, you have to use Fisher's exact test. When they're large enough, you're usually fine using the chi-squared test. It's easier if you're having to do it by hand, but for us, it really doesn't matter. It's a matter of a button click. So in general, just follow whatever you're told to do in your homework problems. They will tell you either to use the chi-squared test or to use, if they want you to use Fisher's test, they say so, basically. So only use it if they tell you to. And otherwise, go ahead and use the chi-squared test, and it will be a close enough approximation to get just a fine answer.